This presentation will cover the concepts of molar mass, percent composition, and then the discovery of empirical and molecular formulas. I'm not going to say too much about molar mass. For many of you, you find it extremely easy. It's the mass of 1 mole of a substance. Basically, it tells you the number of grams that are in 1 mole. We use it to convert between grams and moles, which you will see in the next video. And if you don't know the molar mass of a substance, then it can be found using a mass spectrometer. Percent composition is the mass percentages of every element in the compound. Basically, when you want to calculate a percent composition and you want to know what's the percent of carbon in a compound, then you total up the mass of carbon in the compound and then you put it over the mass of the total compound and times by 100%. Basically what you can do is you can look at mass percent of a element like A as the number of grams of A in 100 grams of that compound. So if it's 12%, then you have 12 grams of A in 100 grams of that compound. Now here's an example question. Calculate the mass percentages of the elements in formaldehyde. Give your answers to 3 significant figures. The first thing you need to do is total up the whole. Okay, now when I do molar mass, all I need you guys to do is 1 decimal's worth. So like carbon on the periodic table is 12.0, hydrogen is 1.0, but you have 2 of them, so that's 2.0, and oxygen is 16.0. Add up 2, 16, and 12, and you end up with 30. So the total mass for that compound is 30 grams per mole. Now, when you want to know the mass percentage of each element, let's do carbon first. You take the grams of carbon, you put it over the whole, and you times by 100. In this case, with 3 significant figures, like the question asked, you end up getting 40.0. And then when you label it, you need to write percent, and not just percent, the percent of what it is for, so percent carbon. Hydrogen would be 2.0. divided by 30 times by 100. We need, again, 3 significant figures, so it rounds to 6.67% hydrogen. And then for the last one, 16.0 divided by 30 times by 100, you end up getting 53.3% oxygen. Okay? Now, the next one's a little bit different. It wants to know how many grams of carbon are there in 83.5 grams of formaldehyde. Now remember, percent composition is based on the fact that you would have 100 grams of the compound, and you don't. In this case, you only have 83.5 grams of formaldehyde. It also says to use the percent composition from the previous example. Since we're worried about carbon, look back at the previous example and you know that 40% of formaldehyde by mass is carbon. So the question is, what's 40% of 83.5? And you'll have your answer. So 40% in a decimal times by 83.5. I'm going to stick with 3 sig figs, and I end up getting 33.4 grams carbon. And I'm done. It's really that simple. Now, just to talk about mass spec a little more, when you analyze compounds with mass spectrometry instead of elements, it's a lot more complicated. Every compound will produce a fingerprint mass spectrum. So what that means is it's unique to that compound. So when you have an unknown and you run its mass spec, we actually have catalogs of mass spectrums that you can look at to compare the mass spec you get to that of known compounds. That way you can identify your unknown by looking at its mass spectrometry fingerprint. The most intense peaks at the greatest mass, so in this case, greatest mass is over here. The most intense are 84 and 86. Those usually will correspond to the molecular mass. Okay, so you can use that if AP for some reason gives you a mass spec. Look at the highest mass ratio there and you can figure out why. Now, the difference between these 2 peaks and why, how do you know which one's which, is because of isotopes. Now, the last topic is empirical and molecular formula. To remind you, empirical formula is the simplest formula for a compound. It has already been reduced. It has the smallest whole number subscripts. Molecular is either the same as the empirical or a multiple of the empirical, which just means this is how it actually exists in nature. Okay, it's a multiple. So if you look at my examples, CH3 versus C2H6. CH3 cannot be reduced any further. It's already been reduced. So CH3 is an empirical formula. C2H6 is the actual formula of, you should be able to figure it out now, that would be ethane, C2H6. So there's the difference. One's been reduced, one is not. And if my next example you look, let's say NH4NO3 is your empirical formula, well, let's say it's your molecular, you can't reduce that anymore. So it would be the same empirical and molecular for ammonium nitrate because it can't reduce the subscripts on ammonium nitrate. When you want to find the empirical formula, there are a lot of steps. The first thing you need to do is turn the given percent composition data into grams of that element. That's nothing more than saying if it's 20% C, we're going to assume we have 100 grams of that compound, like I talked about earlier. So automatically you have 20 grams of carbon. You then convert grams to moles, and then you divide by the smallest number of moles. Now hopefully you get a whole number, like 1, 2, 3. But if you end up getting something that ends in 0.5, like 3.5 or 2.5, then you have to multiply by 2, everything by 2. If you get numbers that end in 0.25 or 0.75, you got to multiply all numbers by 4. And if you get something that ends in 0.33 or 0.67, multiply all numbers by 3. Now, when you finish this, you're going to know how many atoms there are in the empirical formula. So here's an example. An analysis of sodium dichromate gives the following mass percentages. What is the empirical formula? Step 1, convert each of these to grams. So 17.5 grams of Na, 39.7 grams of Cr, and 42.8 grams oxygen. Convert them all to moles. Now to do that you need their molar masses, so you need to look at a periodic table. The molar mass of sodium happens to be 23.0 grams for every mole. Chromium happens to be 52.0 grams for every mole. And oxygen, okay, although oxygen is diatomic, keep in mind that in this case it's bonded to sodium and chromium. So do not use atomic mass. Use the singular mass, which is 16.0 grams of oxygen for every mole. No diatomics. Okay, not when you do empirical and molecular. Get out a calculator, start dividing. When you get the number of moles, do not round for significant figures. Keep more digits than you think are necessary to ensure that your answer is correct. In this case, you get 0.7608695,652 moles. In the second case, you get 0.7634615,385 moles. And in the last one, you get 2.675. Now you divide them all by the smallest and make sure you double check which one is the smallest. The smallest here happens to be the first one, 0.7608695,652. That comes out to be 1. 0.7608695,652. It's roughly 1. 0.7608695,652, and I get 3.5. So what do you do when it ends in 0.5? You multiply them all by 2. When you multiply them all by 2, the very first line was all for sodium. You now have 2 sodiums. The second line was for chromium. You now have 2 chromiums. And the last line of work was for oxygen. 3.5 times 2 is 7, and this is your empirical formula. Now when you want to find a molecular formula, it's a little more intense. Step 1, find the empirical. If they don't give it to you, you have to do all those steps I just did. You're going to then total up the molar mass of the empirical formula, And then since the molecular formula is a multiple of the empirical, you need to figure out how many times larger it is by dividing the molar mass of the molecule, which they give you, by the mass of the empirical formula. You will get a whole number. When you get a whole number, when you divide, multiply the subscripts of the empirical by that whole number to get your molecular formula. So here's an example. The percent composition of acetic acid is 39.9% carbon, 6.7% hydrogen, and 53.4% oxygen. The molecular mass of acetic acid was determined by experiment to be 60 atomic mass units. What is its molecular formula? Do you have the empirical? Unfortunately, you do not. That means you start by converting the percents to grams. So 39.9 grams carbon, 6.7 grams hydrogen, 53.4 grams oxygen. Then convert to moles. A mole of carbon happens to be 12 grams of carbon. A mole of hydrogen happens to be 1 gram of hydrogen. A mole of oxygen happens to be 16.0 grams. Divide them all. Do not round. You get 3.325 moles of carbon. You get 6.7 moles of hydrogen. You get 3.3375 moles oxygen. Then proceed like we just did for the last problem. Divide them all by the smallest. Of the three of them, the smallest is the first one. So to divide by that one. Using the calculator, I find out that the first one is obviously 1 when you divide something by itself. The second one is 2, and the third one is 1. Now this only gives me my empirical formula. My empirical formula is CH2O. But I'm not done. That was just step 1. Now I'm going to go to the next slide so I have room to work. For the next step, you have to total, the molar mass of the empirical formula that we just found. So just to remind you, the empirical formula was CH2O. I need the molar mass of this. Carbon is 12, 2 hydrogens is 2, oxygen is 16. Total them up and I get 30 as my molar mass of my empirical formula. Take the mass that they gave you in the problem, which was 60, put that one on the top, so the given mass goes on the top. The one you just got goes on the bottom. 60 divided by 30 is 2. That tells you that your molecular formula is twice the size of your empirical formula. So when you multiply the subscripts of the empirical by 2, you're going to get the molecular, C2H4O2. And then you're done. Don't forget to answer the quiz for this set of notes, and I will see you soon.